All right, we're going to take a quick look today at something that's called flux. Flux is pretty easy to understand if you're talking about something like rain, where, of course, rain, imagine there's a bunch of rain coming straight down, and if you wanted to catch the most, what you would want to do is put this surface at the top of the cup, of course, oriented like this, and then as you turn to the cup this way, if the rain's coming down, there'd be less and less flux through the top of the cup and into the cup. And then once you got to this orientation, there would be no flux at all through this top ring or into the cup. And so the sort of the handles that you'd have to control how much flux of rain through this area, through this ring would be. One would be how big is this area? How much area are you actually showing to the rain? And then the other thing would be how hard is it raining? And so that's one context of flux. Another one that we can look at is in this example that I put on page 79 that says, there's some bees flying around. It says the flow of bees may be written like this, and it says 3 bees per centimeter squared per second x hat. And so what that means is the bees are all flying this way. Okay, so you got to imagine everybody's flying like this. And then what we're supposed to figure out is the flux of bees that would be through like a picture frame, a 6x5 frame that's held in some different orientations. And so the first way to orient it, it says in the YZ plane. And so then that would be holding the picture frame kind of like this, which is actually the best way to catch the bees, because you've got the bees all going in the X direction, you've got this frame, and so the best way to capture them, is to just hold this thing perpendicular to the way that they're going. So one definition of what's called flux that we're going to write like this, capital Phi, Greek letter Phi for flux, looks like a sideways TIE fighter, something. One way to calculate flux is, we'll write it like this, F Aperp. So you'll have some kind of a vector field, in this case, which is a flow of bees, times area that you present perpendicular to the vector field. And so in this case, it's going to be 3 times, and then the area here is 6x5 or 30. That's the area that you've shown perpendicular to the bees. And so what's going to happen is you're going to get 90 bees per second. Okay, so that's one way to do this part. Another way to visualize this, that's also a way to define flux, is we could also have written it like this. It's called F dot A. Right, so we're just going to redo this in a slightly different way. So what you would want to do here is F is given, it's the vector field that we want to find the flux of, and the area, this is new, what this area vector is it has magnitude equal to the area, and it's just perpendicular to the area. So in other words, in this orientation, this A vector has magnitude 30, and it goes that way. So 30 x hat, let's say, that's going to be the area vector. And so if we find the flux in this way, what we would do is we'd say, well, the flow of bees is like 300, and that area vector is going to be 3000. And so you notice if you then take the dot product, it would be 90, 3 times 30 is 90, plus 0, plus 0. And so then that's again going to be 90, bees per second. Now I haven't really shown you how to decide whether this vector points to the right or to the left. We'll learn how to orient it later. But the big thing I want you to remember is this area vector has magnitude, that's the size of the area, and the direction is just perpendicular to the area itself. So in either case you get 90, okay? So that's kind of like part A. Let's do the next part, which I think you can see what it's going to be already, but just to kind of quick talk it through. It says in the XZ plane for part B. What that would mean is putting the picture frame down here like this. And you can tell that you're not going to catch any bees. Like, that's the worst way to hold the thing if your goal is to try to catch these things. Well, a couple ways to see it. One is that there's absolutely no area that's being shown or presented to the bees. And so for part B there, if you try to do flux as F Aperp, your Aperp is basically going to be 0. So you'd have like, 3 B's times 0 is no B's, right? So there's not going to be any flux. The other way to do it is if you did F dot A. Your F vector, of course, is still 3, 0, 0. Now what's going on is your A vector, for part B here, if you're orienting the frame like this, your A vector is going to point, again, perpendicular to the frame, or it would be like 30 y hat in this case. So in this case, the area vector would be 30 y hat. It's got magnitude equal to the area of the frame, and then it just points in the y hat direction. So, or you could say in the minus y hat direction. So if you dot these vectors together, this would be like 0, 30, 0, or minus 30. Doesn't matter whether it points up or down. You'll see you get 3 times 0, which is 0, plus 0 times 30, which is 0, plus 0 times 0. So again, you get no B's in that case. So that's looking at it either as F Aperp or F dot A. Finally, if you look at part C here, the last example, we have the picture frame kind of oriented like this. What I personally see right away, like my vision of Flux, is I would see this particular problem fastest using this F Aperp version of Flux. And what you basically want to do is you really only care about the area that's being presented perpendicular to the B's. So you really just want this shadow of the frame here, because that's really what the B's are going through. And you can kind of tell that you're just taking the shadow of this thing down onto the YZ plane. So you can see that's really just going to be this area times, right, cosine 70. And so then what we can do is say, well, the B's, flow of B's has magnitude 3, and then the area that's perpendicular to this is going to be 90, but then we want to take the cosine of 70 degrees to project the shadow down. Excuse me, that's 30, 3 times 30. And so that's going to be 90 cos 70. And so I'll just quickly get that on a calculator. So if we go 90 cosine of 70 degrees, hopefully I'm in degrees on this thing, we get 30.8 B's, let's say. So 30.8 B's per second. Okay. The other way to see this one would be with that F dot A. Well, so the key here is we have to figure out which way the area vector points. So one way to see this one's a little bit tricky, but if you imagine looking down the y-axis, so that the frame kind of looks like this. Here's the x-axis, and here's z. And what you have to imagine is looking down from here, right? So here's your x and z axis, but if you look down from above, they're going to kind of look like this. Then your picture frame is going to be set like this, where this is 70 degrees. And then what's going on is this area vector here is magnitude 30, but we need to get its, we need to write it in terms of x, y, and z like coordinates. And so what we could see is that in the x direction, right, so this thing would have been, if this picture frame were rotated or all the way down here, it would have pointed like this. Well, we've cranked it up by, this thing up by 70 degrees. So let's see, if that is 70, then that means that this thing would be like 70 here also. This arrow has been cranked up by 70 degrees from the horizontal. And so what we would do is we could say, well, flux is F dot A. And so then that's going to be, let's write our F vector is going to be 3, 0, 0 again. And then here's the tricky part, the A vector. Well, the X component is going to be like 30 cosine 70, right? Because this thing has magnitude 30, and we just need to take a little bit of it that happens to point this way. So that's going to be 30 cos 70. Now we basically already have the answer, but just for finishing this up, the y component would be 0, because it doesn't point it doesn't point in any at all in the y direction. And then the z component is actually negative, and it would be 30 sine 70. So it'd be like minus 30, and sorry I'm getting so low on the board. That's very messy. Minus 30 sine 70, that says. But it doesn't matter anyway, because when we take the dot product, it's gonna go away. So you notice you get 90 cos 70, as we got before actually, and then 0 and 0 when you take the dot product. And so then that's also gonna be 30.8 V's per second. So that's flux. I use this vision of it the most, I would say, but this is kind of a more formal definition for flux through an area.